Okay, in this video I'd like to share with you how we will label and identify transformations and talk about how they're going to apply to not only parent functions but any function that we encounter in this class. Before I get too far, I do want to give you an idea of what's happening in the next week or so with regards to test number 4. On Friday of this week, we're going to complete a take-home practice test. Actually, I'll give it to you towards the end of the day on Friday so that you can work on it over the weekend. Then when we see each other the following Monday, we will review the practice test together, and I'll also answer any questions that you might have that came up during the Math Excel review or on the test itself. And then on Tuesday, we'll complete the no calculator portion of test number 4, and on Wednesday, we'll complete the calculator permitted portion of test number 4. So I just wanted to share that with you since I'm not in class today. You have an idea of what to look out for in the upcoming weeks. And as far as transformations go, there are basically 3 different types of transformations that we encounter: shifts, stretches, and flips, or any combination of those. And for this class, it's important to note that shifts can be either horizontal or vertical. And to account for a vertical shift, to account for a horizontal shift, what we're going to do is we're going to apply either adding or subtracting. I'm writing subtracting here just to make a point that I'll talk more about here in a minute, but we can add or subtract a constant value on the interior of a grouping symbol for a particular function. Now I'm using a generic function notation here, f of x, but keep in mind our parent functions from last week. If we've got the parent function of a quadratic, y equals x squared, then an example of a horizontal shift might look something like this: y equals x minus 2 squared. And a horizontal shift of this parent function can be accomplished by subtracting 2 on the interior of a grouping symbol. Similarly, if I write y equals x squared plus 2 on the outside, well, here again, we're completing a shift, but in this case, it's not horizontal, but it is vertical. Oops, you got a preview of the practice test that's coming up. So again, this is a vertical shift because the constant this time is on the exterior of our grouping symbol. Now you'll notice too that shifts occur when we add or subtract a constant to the function. A stretch will occur when we multiply a constant by a function. Now the horizontal stretch occurs when you multiply on the interior of the function's argument, and the vertical stretch will occur when you multiply on the exterior of the function's grouping symbol. Lastly, a flip will occur when not only are you multiplying by a number, but it happens to be a negative number. So horizontal flips occur when you multiply by a negative number on the interior of a grouping symbol, and a vertical flip will occur when you multiply by a negative number on the exterior of our grouping symbol. Now hopefully you've started to notice or you recall these similarities from another class. But anytime we want to perform some sort of horizontal change, a horizontal transformation to a function, those all occurred on the inner portion of the function, the inside of a grouping symbol. If we wanted to perform some sort of vertical transformation, then all of these computations occur on the outside, or on the outer portion of our function. So by recognizing that pattern, it's going to make computing your or establishing your transformations a little bit easier down the road. Now we will talk more about specific parent functions and how they transform a little bit later this week, but for right now in this video I'd like to just illustrate that these transformations can occur regardless of what the function is defined as. So here we have a graph of a function. It's this kind of weird looking shape here. There's a horizontal bar and then a diagonal bar or component associated with it. But that's the result of our function. That's the graph of f of x. On the remaining axes, we've got 8 more to look at. We would like for you to sketch the transformations as follows. So in part A, I want you to show me what the function would look like when transformed using this command. Now, until you have this memorized, you may end up referring back to these rules, but I'll point out that we have the original function f of x minus 2. And since the subtraction of 2 is on the outside of a grouping symbol, that's going to represent a vertical shift. And as you might expect when applying a vertical shift, the number indicates the direction of the movement. So the function f of x has been moved down 2 units. Sometimes I find it helpful to use a dotted line or a real faint sketch of where the original function is, so that when I draw the final answer, or when I draw my final answer, I can double check to make sure that the transformations that I'm applying do match exactly what I expected them to be. So here we go. There's the graph that's been shifted down 2 units, and I think that's a good design for part A. For part B, we're being asked to sketch this function, f of x minus 2. This time the subtraction is on the interior of the grouping symbol. So if we're subtracting on the interior of the grouping symbol, that's a horizontal shift. And what I need to point out here is that horizontal shifts always perform in the opposite manner to which you might expect. So and that's the reason why I'm writing this x minus h here, by the way. When we subtract 2, a lot of you might think, well, subtracting 2, that means it's going to shift to the left 2. But in actuality, that's not what happens. This function will actually be shifted to the right 2. So I have my dotted line that represents where my original function was, and I need to make sure that I sketch this 2 units to the right. So here and here. Now with this electronic ink, that could be a bit distracting, so I'll go ahead and erase it. But if you're doing this on your paper and writing lightly, I don't think it'll be as much of a distraction. For question C, we have the function f of x with a negative sign in front of it. So this negative sign in front, it's outside of the grouping symbol, so I know it's a vertical change, and the negative symbol does indicate a flip. So for part C, we need to flip this original function vertically. Now when we talk about flips, we are talking about flips over an axis. So this is over the x-axis, and if I flip this vertically over or about the x-axis, the end result should look something like this. Now here again, the dotted line might be a bit distracting, so I will erase that. But this sketch here will represent the opposite, or negative, f of x. Part D asks us to do the same thing. This time the negative sign is on the interior. So hopefully by now you're starting to recognize the behavior of these transformations. And the negative sign on the interior does require a horizontal flip. So any point that exists on the original function has to be flipped horizontally across the y-axis. So this coordinate here is going to get flipped all the way over to this point. This one here gets flipped over to here. And all of the others in between get flipped as well. So this one flips to this side. This one stays put where it is. Now many of you will probably recognize what the result should be without having to consider each of these individual points, but I did want to put that out there just in case you do need to consider them, or if you need a technique that works better for you. So I think that sketch for part D does a nice job of describing the horizontal flip. For part E, we have a number on the exterior of the grouping symbol. So that means it's a vertical transformation. And when we multiply by a number, then that's going to create a vertical stretch. Now 2 in this case is the factor of the vertical stretch. So if we had, a picture that originally existed right here, this was the original function, what I might consider doing is multiplying each of the y values of some of these key data points by 2. So I would consider this a key data point, this and this definitely key data points, but even these along the way. If you consider the work that we did last week, identifying our key data points, then you would be doing the exact same thing that I am here for those parent functions. The y value in this position is 2, and so if we stretch the graph vertically, the y value has to double into 4. We make no changes to the x values when applying a vertical stretch. The y value here was 2, so we double that into 4. The y value here again is 2, double that to 4. The y value here is 1, we double that to 2. And the y value here is 0, we double that and it remains 0. So now if I connect these with a pair of lines, we see an end result that looks something like this. And here again, I'll eliminate my dotted line that began this process. And you'll notice that this resulting graph is a stretch twice as tall as the original. No changes in the horizontal direction, but the vertical direction has been shifted by a factor of 2. Part F does have a multiplication on the interior, so 2x. But here again, anytime that we make a change on the interior of our grouping symbol, we need to think the opposite. So the opposite of stretching this wider is going to be making it narrower. So for part F, while our original sketch would have looked something like this, the b value of 2 will make this sketch half as wide. So again, I'll consider my key data points. And if I were to focus on the x values and cut them in half, well, this x value is -2, so half of that is -1. I'll use a different color to make this stand out. The green dot that was here, half of -1 is 1/2. Half of an x value of 0 is 0. Half of the x value of 1 is a half. Half of the x value of 2 is 1. And if I connect these blue dots with a straight line, then we'd have ourselves a picture of our transformed function. Factor of 2 on the interior of our grouping symbol multiplied by x means that this graph is now half as wide. Part G and H are a combination of transformations. So we have a +2 on the interior of the function. So this means that we're going to be shifting to the left 2 units. And a 1/2 on the exterior means that we are growing or reducing in size by half in the vertical direction. So let's see what that would look like. Here's our original sketch, and if we consider our key data points, we could then follow the order of operations to perform this transformation. We always do multiplication before addition or subtraction, so the multiplication step will adjust the height of this shape. So the height is going to be 1/2 of the original, shown with these small blue dotted lines. And the +2 is going to force this graph to be shifted to the right 2 units. Each of these key data points that I showed here with the light blue dots have now been moved, or must now be moved, to the right 2 units. And it's this red graph that would represent a transformation of the parent function of 1/2 in the vertical direction and +2 in the horizontal direction. Though as soon as I said that out loud, I caught my mistake here. A +2 on the interior of the function should actually move this graph to the left 2 units. And we even wrote that down on paper here. I just forgot about it. And now the graph in red does indicate the proper transformation. These other markings might be a bit distracting, so I'll go ahead and erase those now. If you'd like to leave those markings or your preliminary work on a test or a quiz, I'd be perfectly fine with that. And now for the last example, we have 2 minus f evaluated at 1/2 of x. Well, this 1/2 on the interior represents a horizontal stretch, and since we're thinking opposites here, a b-value of 1/2 doesn't make it half as wide. It actually makes this 2 times as wide, so 2 times wider. This minus sign, don't forget, is a multiplication of -1, so this is going to be a vertical flip. And we also have a +2 that's being added to the function, so this is going to be a vertical shift. No surprises with the vertical changes. A +2 means that we're going to shift this upward. And a vertical flip, well, we're just going to flip this over the x-axis to obtain the vertical flip. And here again, we would follow the order of operations. And I think in part G, I did the order backwards. I completed this multiplication before this addition. However, this addition is on the interior of a grouping symbol, so we should actually have completed that first. If we look back at our graph, though, I don't think that's going to change anything. If we had shifted to the left 2 units first and then multiplied that by 1/2, we would have ended up in the same position. So I don't think that always works, but I don't think we can go out of order all the time, but in this case it did work out just fine for us. Now here we go in the final example, part H. Here's our original function. The first thing I would like to consider is making this twice as wide. So if we take the key data points on the original function and double each of the x values, we would end up with key data points that ended here. I'm going to erase those so that we don't make too much of a mess on this sketch. But those data points represent the multiplication of 1/2 on the interior. If we were to flip this vertically, because of the negative sign before the addition of 2, we would end up with key data points down here. And lastly, if we complete the vertical shift of +2, then each of these key data points gets moved up 2 units. And the location of our final sketch would be something like this. And here again, if we eliminate the original dotted lines, now we can see what our final result should be. So I realize there's a lot that goes into these transformations if you've never seen them before, but start memorizing your rules here for transformations, and if you've seen this before, hopefully this is coming back to you now. When we see each other next, we'll talk a little bit more about how we can apply these transformations to parent functions, and I'll also show some examples of how we can use the transformations with the key data points that you started to memorize from last week. Thanks for watching.